Hello, my name is Catherine Hughes, and I'm a senior majoring in environmental studies and Spanish here at Randolph-Macon. Over the past 2 years, I've had the opportunity to conduct research with Dr. Michael Fenster in the Environmental Studies program to examine the development status of the world's mixed energy and wave-dominated coastal plain and deltaic barrier islands. First, I wanted to give a brief outline of this presentation. I will begin by defining some key terms and explaining my rationale and objectives behind why I pursued this project. Then I will go into how I identified and selected these barrier islands, delineated the development zone, and established a land classification scheme. Next, I will share the results of the study with varying specificities and finish with concluding statements. For this study, we defined a barrier island as elongated, shore parallel accumulations of sediment separated from the mainland by a back barrier lagoon or marsh. Barriers must have ocean-facing, light-colored, sandy beaches and be bounded on their updrift and downdrift side by tidal inlets. We only included barrier islands and excluded all other types of barriers, such as baymouth barriers and spits. We analyzed barriers in the context of hydrodynamic and geologic setting. This study focuses on two types of barrier islands: wave-dominated and mixed energy. Wave-dominated barriers were identified as islands with elongated, narrower morphology and abundant washover features, such as washover fans and flood tidal deltas. The image to the right is an aerial view of the Outer Banks, its wave-dominated barrier system. Mixed energy barriers were determined by their shorter drumstick or more rounded shape and numerous closely spaced tidal inlets. The image to the right is an example of the mixed energy barrier island chain off of the eastern shore of Virginia. We also considered the influence of geologic setting on density and type of development found on these barrier islands. Coastal plain barriers are defined as islands formed as a result of sediment eroded from the continental shelf or of the mainland. Long Island, New York is an example of a coastal plain barrier system. You can see this in the top image. Deltaic barriers are composed of fluvial sediments that are carried down the river in channels and deposited at the mouth of the river. The mouth of the Dvina River in Russia is a great example that shows examples of deltaic barrier islands. That's the bottom image. Now, because we are proud to be from Virginia, with 11 out of our 12 mixed energy barriers remaining undeveloped, I really wanted to answer the question, does the Virginia Eastern Shore really contain the longest natural expanse of mixed energy barriers? That's where this project began. However, as I began this research, as I began to compare global and local data, I realized that there is no existing data on the density or type of development found in the United States or global barrier island chains. I also wanted to note that our preliminary study only included mixed energy barriers. But after our submission to the Journal of Coastal Research, the reviewers requested that we expanded this data set to include wave-dominated barriers. Primarily, my goal with this study was to quantify density and type of development around the world's barrier islands because this data set does not exist. But I was also curious to see if the hydrodynamic or geologic setting influence density and type of development found on these barriers. So are there more structures on wave-dominated versus coastal plain, or coastal plain or deltaic, or wave-dominated or deltaic? All these different combinations of barrier islands exist. I wanted to see which one was the most development, included the most development. So to begin my analysis, I first had to identify and select barrier island chains around the world. Now, a desktop analysis utilizing remote sensing provides some unique challenges. There is no buoy data available for the entire world, and it's very difficult to interpret barrier islands by morphology only. For example, one of the shortcomings is that it is challenging to discern barrier islands from non-barrier marshlands or relic coastal ridges surrounded by deltaic wetlands. An example is shown to the right, and as you can see, there's cloud cover as well as some features that could maybe be seen as barriers, which is really difficult to distinguish just looking at aerial imagery. And a problem I continuously ran into was a lack of imagery in less developed countries, or low quality, pixelated, or cloud covered data. Despite these obstacles, I use morphology as a proxy for process because there is no global data available that are both spatially and temporally consistent. Now, as a result, I looked through every piece of literature I can get my hands on to define barriers islands by both geologic and hydrodynamic setting, including Hayes 1979, which is this image at the right, and Sutton-Pilkey, which I cited papers from 2002 and 2011. To quantify development, I selected the USGS Anderson classification scheme from 1983. Although it's aged, it has many strengths in that it's based in classifying structures using only aerial imagery. The Anderson scheme has 9 major categories, the first of which is urban or built up land. This category was the only classification that includes intensively used areas that are largely covered by structures. This broad classification is then subdivided into level 2, which includes those listed as 11 through 17 on the right slide. Even finer, level 3 categories took the residential category and separated it into single and multifamily units. Finally, every category was delineated into high and low density areas. The definition of high density in this case is that there are more than one structure per acre of land. Overall, there were a total of 1,007 island measures, and 514 of them were identified as mixed energy, and 493 were identified as wave dominated. In terms of geologic setting, 450 are coastal plain, and 557 were deltaic. These all added up to a total length of 7,690.5 kilometers of shoreline. As I previously mentioned, I use Google Earth aerial imagery to measure the barrier island lengths and distances of dominant classification type. I had to select this wider range of time from 2015 to 2017 because there was a lack of quality imagery in many areas of the world. I used the Google Earth ruler to measure 300 meters away from the ocean facing shoreline, as shown in the figure to the right. We selected this distance because 300 meters exists most V-zone inundation areas that are considered to be in high risk in the United States. So this value serves as a proxy for process for coastal infrastructure vulnerability. This is the same barrier on the coast of Brigantine, New Jersey, but it's zoomed in so I could show different land use classifications. In the pink, this area was classified as single family unit, and it is a neighborhood. But then it stops when this neighborhood ends with the beginning of a parking lot, which is the area in blue. This area in blue is the commercial and services area marked by the parking lot and structures associated with the shopping mall, all within 300 meters of the shoreline. Now, this figure shows all of the barrier islands around the world that were included in this study by degree of development. Getting into the results, I wanted to start at a global scale and then zoom in. The highest average development value by political boundary was about 50%, and the lowest value representing those barriers that remain completely undeveloped within 300 meters of shoreline is in green. 33% of all barriers were classified as coastal plain wave dominated. This was the dominant barrier island type in the world. I found that 20.7% of all barriers have some type of development on their shoreline, but 18.8% of all barriers are completely undeveloped. The following areas provide an opportunity for research with minimal or no human influence. In terms of coastal plain geologic setting, Australia, specifically the coast of the Gulf of Carpentaria along the coast, and west coast of Madagascar. And then the Copper River, Indus, and San Juan deltas provide a great place for further studies in deltaic barrier island systems. Overall, I did find that single family high density land use was the dominant classification type. And residential land use dominated all shorelines. This graph shows the total length of barrier islands by country compared to the total percent development for these countries. The top 3 most developed countries in the world are the United States, Italy, and Vietnam. However, it is important to note that Italy and Vietnam have disproportionately smaller shoreline lengths, but they're highly developed. And the United States has at least twice as much shoreline as any other country in the world by an order of magnitude. And it was an anomaly in the overall results. The United States really stood out in this study in that it contained 41.2% of all global barrier shoreline lengths, with wave-dominated shorelines predominating. There were 107 wave-dominated versus 104 mixed energy barriers. This isn't a huge margin, but it was important to note that there were more wave-dominated than mixed energy barriers along the United States. The US contributes 70.6 of all global development. And more specifically, the East Coast contains 76.5 of all development in the United States and 54% of all global development. In the United States, the development per region or per state is higher than any other region in the entire world. This figure shows the summary of percent development to total length of barriers in the United States. Florida and New Jersey stand out as the most developed barrier systems, while Rhode Island is the only state with 0% development on its barrier shorelines. I wanted to zoom into the United States East Coast because it stood out as containing the most lengths and development in the United States and in the world. Overall, the Southeast is more developed with 44.8% average development than in the Northeast with 37.1% development. To the right, this is the graph of Florida's breakdown of development. It is the Southeast's longest barrier chain and the most developed with 72.7% average development per barrier. In the North, New Jersey is the Northeast's longest barrier chain and it's 66.5% development per barrier. And also notable is that New York contains the highest value of transportation, communication, and utilities in the world. This means that within 300 meters of the shoreline, there were structures associated with highways, airports, or other utilities, such as parking lots right on the beach. In conclusion, I found that coastal plain barriers are more developed than deltaic barriers, and mixed energy barriers are more developed than wave-dominated. Residential land use is the dominant type of land use around the world, and the United States contains the most development worldwide by a landslide. The East Coast barriers of the United States are especially significant because they make up over half, 53% of global development. This study emphasizes the importance of future policies and management strategies, especially along the East Coast of the United States. With this study, we really hope to stimulate further work. I would really like to continue quantifying development along other types of barrier and coastal systems, including other barrier features such as tide-dominated or spit features. And it is important to note that we would like to continue to monitor changes in land use over time. Thank you for listening. If you have any questions, please reach out to either myself or Dr. Fenster. We would love to talk with you.